In this tutorial, we're going to be talking about chemical reactions. The first concept that we need to understand for a chemical reaction is stoichiometry. Stoichiometry is the theory of the proportions in which the chemical species combines with one another. So we have an equation, and the stoichiometric equation has to be balanced. Let's say that you know that you have sulfur dioxide, and you know that this is going to combine with oxygen in order to produce sulfide trioxide. The first thing that you need to do in order for this equation to be valid is to balance. And the same amount of sulfurs that you are going to have at the left part of the equation is the same amount that you will have at the right, and the same with oxygen. Now you have 4 oxygens at the left, and you have 3 at the right. So in order to solve this problem, you are going to be inputting a 2 into the 2 sulfur oxides. In this case, you're going to be having 2 amounts of sulfur and 6 of oxygen. Here you will have 2 sulfurs and 6 oxygen. So this is to balance these 2 numbers. Here you have a 1, although it's not expressed. And you have also in this side a 2. This is what we call a stoichiometry coefficient. This information will tell us that 2 moles of sulfur dioxide is going to react with 1 mole of oxygen in order to produce 2 moles of sulfur trioxide. So whenever you have the reaction, the first thing that you need to understand is that everything has to be expressed in moles. If something is given in grams, then use the relationship where number of moles is the mass over the molar mass or the molecular weight. In order to convert this into moles, you are going to be working the reactions only in moles. Let's suppose that we have a reactor and we feed into the reactor, let's say 2 moles of SO2, and we feed here into the reactor, let's say 1.5 moles of O2. The limiting reactant is the one that it's going to be totally consumed when the chemical reaction is complete. In order to obtain this limiting reactant, we're going to divide the moles that we feed into the reactor, and we're going to divide them into the stoichiometric coefficient. So if we are going to feed 2 moles of SO2, we divide this into the stoichiometric coefficient of SO2, which is 2. This gives us 1. While if we're going to feed 1.5 moles of O2, we're going to divide this into the stoichiometric coefficient, which is 1, and we're going to have here 1.5. The fact that this number is less in the SO2 will state that this is the limiting reactant, while the other is in excess. If both of them are stoichiometrically the same, or these 2 numbers are exactly the same, then there is no limiting and there is no excess. Everything is stoichiometric. But one has to be the limiting reactant, and it's compared with the fed over the stoichiometric coefficient. Since the sulfur dioxide is the one that is limiting, in order to determine the amount of oxygen that will react, we're going to grab the 2 moles fed of SO2. We're going to divide that over its stoichiometric coefficient, the stoichiometric coefficient of SO2, the limiting reactant, and we're going to multiply that times the stoichiometric coefficient of the oxygen, obtaining here that we're going to need 1 mole of O2, stoichiometrically speaking, that is going to react with SO2. We can define the fractional excess as the amount of moles that are fed minus the amount of moles that we need stoichiometrically over the amount of moles that we need stoichiometrically. In this case, for the O2, since we're feeding 1.5, we're going to subtract the 1 that we have already obtained before over 1, and then we will have here 1.5 minus 1 is 0.5 over 1. We will have a fractional excess of 0.5, which is the 50% of excess that we have of the excess reactant. The limiting reactant has no fractional excess. We define the fractional conversion as the moles that reactor over the moles that we fed. We can say that 100% of the moles of SO2 reacted, so that's a fractional conversion of 1. And in such case, the fractional conversion for the O2 is the amount of moles that reacted, 1 in this case, over the amount of moles that we fed, 1.5. So the fractional conversion for O2 is going to be equal to 0.67, or the 67% of this reacted. Not always the fractional conversion is 100% for the limiting reactant, but we can actually state that there is a fractional conversion so that we can see how many moles reacted. In order to obtain the amount of moles that are going to be consumed of the reactants and the amount of moles that we're going to produce of the products, we're going to state the advance of reaction. The advance of reaction is going to be the amount of moles that are going to react of the limiting reactant, but this is going to be standardized for 1. Since the limiting reactant is SO2, we can say that the amount of moles that react is 2. We're going to divide that 2, the amount of moles fed, over its stoichiometric coefficient, and we're going to obtain what is called the advance of reaction. It's going to be expressed with this symbol. If the 2 moles that are fed are not the ones that react, but because there is a fractional conversion, we still do the same. Let's suppose that the fractional conversion for this is 0.7 of the limiting reactant. It means that the amount of moles that are going to react here is going to be 0.7 times the 2 moles that are fed, which is equal to 1.4. So we're going to obtain the extent of the reaction, or the advance of reaction, which is the same, by dividing these 1.4 moles that reacted over 2, obtaining 0.7. These are the 0.7 moles that are going to be reacting. That is going to be the advance of the reaction. It is obtained by the amount of moles of limiting reactant that reacted over its stoichiometric coefficient. In order to get the final moles, we're going to grab the initial moles, plus minus, plus when we have a product, minus when we have a reactant, the stoichiometric coefficient times the advance of the reaction. For SO2, we're going to state that the final moles of SO2 is going to be the 2 moles that we fed, minus, because this is a reactant, the stoichiometric coefficient, which is 2, times the advance of the reaction. In the previous example, we stated that the advance of reaction was 0.7. So in this sense, we're going to have 2 minus 1.4, 0.6 moles we're going to have at the very end of SO2. What happens with oxygen? We're going to have 1.5 minus 1 times 0.7. We're going to have 0.8 moles of oxygen. So we can have an output which is also the reactants, because they didn't react all of them. What happens with the products? For the products, we're going to have that we don't have an input of SO3. We will have 2 times 0.7, so it will yield to 1.4 moles of SO3, which were produced during this reaction. That's how we get the final moles after the reaction has occurred. The yield of a reaction is defined as the amount of product that we obtained over the amount of product that we predicted. Let's say that for SO3, we predicted that we were going to obtain 1.4, but we actually obtained, so that's information that we can actually go and weigh, or we can actually measure. We actually obtained 0.7. That would mean that we will have a 0.5 of yield, or 50% of the yield for this reaction, which means that not everything is how we expected.